Okay, hello again. Welcome to Terrestrial Planets Part 2. This lecture will focus on Venus. Just a little reminder, if it's been a while since you watched the first lecture on this, of where we are, where we're talking about. So this is a little toy model of the solar system, and right here, the inner planets are the terrestrial planets we're talking about today. Last lecture, we talked about Mercury, and today we're going to talk about Venus. Again, just a little reminder of kind of the characteristics of the region that we're talking about. The inner 3AU, solid bodies with rocky mantles and metallic cores, probably had very similar formation mechanisms. Okay, so this lecture we will talk about the second planet from the sun, which is Venus. She's about 67 million miles away from our star and has some superficial similarities to Earth. The diameter of Venus is about 7,500 miles versus or 7,500 miles versus 7,900 miles for Earth. So about a 400-mile difference in the diameters. Venus has a thick atmosphere, and from what few missions we've taken to this planet, we've gleaned that Earth and Venus are probably actually made of very similar things. So for a long time, Venus, kind of like Mars, was hypothesized to be habitable, and not only habitable, but inhabited. Also, like Mars, this turns out not to be true. We'll talk a little bit more about Mars later. In fact, the size and bulk composition are likely to be some of the few things Earth and Venus have in common. It turns out there's not a heck of a lot more. So Venus has a very small, very little axial tilt. So there's no real seasons there to speak of, at least as we experience them here. Earth's axis, of course, is tilted 23.5 degrees. And this means that sometimes one hemisphere is pointed toward the sun, the other is pointed away. We've talked extensively about that in previous lectures. So again, when your hemisphere is pointed towards the sun, you get summer, and pointed away, you get winter. And the tilt of Venus's axis is only about 3 degrees, so there's no seasons. Since Venus, though, rotates a little bit differently. It rotates clockwise instead of anti-clockwise, like the rest of the planets. Sometimes its tilt is actually described not as only 3 degrees, but as really of almost 180 degrees, right? 177, really the most extreme tilt in the solar system. So this is a comparison of Earth's tilt, the tilt of Uranus, which is about 90 degrees. This planet spinning on its side, which we'll look at a little bit later, and Venus's tilt. So you can kind of see where they're coming from, right? The North Pole has kind of been flipped to the bottom, but functionally we have a planet here that's basically kind of straight up and down, which means Venus has no real seasonal variation. So this combined with Venus's thick atmosphere of almost entirely carbon dioxide means that the planet is very hot all of the time. Venus hosts a thick atmosphere with clouds of sulfuric acid. Um, so that would kind of make the entire planet smell like rotten eggs. The CO2 atmosphere causes a runaway greenhouse effect, which we'll discuss a little bit in a second. So the surface temperature is about 850 to 900 degrees Fahrenheit. So it's literally hot enough to melt lead, and it's like this all the time. If the heat doesn't get you, the pressure will. The pressure on the surface of Venus is 90 times what it is at sea level on Earth. So the atmosphere itself will literally crush you. Since Venus is covered in thick clouds, it's very difficult to see what the surface looks like. But thanks to limited surface studies and radar studies, we do know a little bit about the surface of this planet. One thing that planetary scientists have measured that tells us a great deal about the interior of Venus is its magnetic field, or rather, its lack of a magnetic field. Venus is presumed to have an iron nickel core like Earth. This is reasonable. Iron and nickel are heavy, meaning that over time they will sink to the center of the planet. Remember that process called differentiation? We don't have seismic data for Venus, kind of like how the planet trembles. Um, so what we think we know about the interior of the planet comes mostly from planetary models. We know that Venus and Earth have a similar size and density, so the assumption is that they have a similar composition. Yet Venus does not have a magnetic field like Earth does. So astronomers think that the surface of Venus is also geographically very young because there are very few craters. There could be a few craters. There could be few craters because of Venus's really big, thick atmosphere. Small craters that we've seen are irregular and appear in groups, which indicate that the atmosphere is really slowing down and breaking up potential impactors. There are also few large craters, and those that we do see look pretty young. They haven't filled up with lava, and radar data indicates that they're rough and haven't had time to be eroded. So it could be that the atmosphere just slows down all the big impactors, but the bigger factor is thought to be um, a catastrophic resurfacing event on the planet's surface. So in planetary geology, crater counting is actually a pretty tried and true way of estimating the age of the surface of a planet or a moon. So based on this method, Mercury, Mars, and the Moon have much older surfaces than Venus does. So for reference, these are crater maps of Venus and Mercury. So you have Venus on the top here, Mercury on the bottom, the subject of the last lecture. And you can see there's just way more craters on Mercury than there are on Venus. They're much different. And this is weird because Venus doesn't actually have plate tectonics like Earth does, um, which is a way of kind of recycling the planet's crust, right? That thin outer layer. So if there's no plate tectonics, we really would expect to see more craters than we do see on Venus's surface. So what planetary scientists think may have happened is that Venus underwent what is called a global resurfacing event between 300 and 500 million years ago that literally kind of paved over all the old craters. On Earth, plate tectonics not only recycles the planet's crust, it also allows heat to escape from the mantle by transporting the mantle material to the surface and returning old crust into the mantle in a process called advection. But Venus has no plate tectonics, so how does this heat escape? Because of the decay of radioactive elements that just exists naturally, the interior of Venus continues to heat up. And it will continue to heat up until the mantle is hot enough to force its way to the surface and will essentially resurfaces the entire planet. So Venus is covered with lava until the mantle cools enough for the entire process to start over. So this is a theory, it's a hypothesis, like a lot of things to do with Venus. We don't have a lot of data from the planet's surface, but it is one way of kind of explaining why the surface of Venus looks the way it does. Regardless of whether the hypothesis of global resurfacing is found to be correct in whole or in part, volcanoes have been integral in shaping the surface of Venus. So Venus, the surface is really a mosaic of different lava plains. So there are over 1,000 volcanic structures on the planet, but we don't know for sure if any are currently active. The best we can tell for sure is that volcanoes on Venus definitely erupted 2.5 million years ago, but there's no absolute evidence that any of Venus's over 1,000 volcanoes have erupted recently. But there have been little hints that mainly involve kind of changes in the landscape of Venus that we've measured over time. Like some of these, there's a change in the sulfur dioxide over the past 30 years, which is something, an effect of an erupting volcano. Um, there are some images here, some radar images um, that indicate some changes um, in a volcanic vent. Some hot spots that we've measured also seem to be changing. So there's some of this indirect evidence that there's still volcanic activity, but no smoking gun quite yet, so to speak. Probably one of the biggest questions motivating scientists to study Venus is really how Venus got to be the way it is. Venus, as I mentioned before, is a similar size and density to Earth. Venus is right on the edge of the sun's habitable zone, so where kind of liquid water could theoretically be in the right circumstances. So, what happened to send Venus and Earth on such different paths? So, here's what we know. We know that the atmosphere of Venus is about 95% carbon dioxide, which is a potent greenhouse gas. We know that is also trace amounts of water in the atmosphere. We know that Venus at least was volcanically active in the past, and that volcanoes can emit CO2. It seems as though Venus has experienced a runaway greenhouse effect that made the planet absolutely unlivable on the surface for life as we know it. But how did this come to be? And there are basically two broad options, like two broad theories, hypotheses, so as to what happened. So the first possibility is that Venus had oceans, and those oceans were boiled off by the sun. So Venus is closer to the sun than Earth, and young stars can get hotter and brighter more quickly than the fairly quiet middle-aged star that our sun is now. It's possible that the sun got a little too hot a little too quickly and caused Venus's oceans to evaporate. So water vapor is also a greenhouse gas. It's not the primary cause of our greenhouse gas problems on Earth, but if you have a lot of water vapor in the atmosphere, it will trap heat. Now, imagine an ocean's worth of water vapor in the atmosphere. It's possible that this water vapor may have kicked off a runaway greenhouse effect, and CO2 from volcanoes just finished it off. Possibility two lays blame on volcanoes that literally broke Venus's plate tectonics. So to understand this, you have to think about a big extinction event on Earth called the Great Dying. About 250 million years ago, volcanic fissures opened up in Siberia and created a continent-sized flood of lava. This event caused a chain reaction during which 90 to 95% of all species on Earth were killed. It took 2 million years to stop erupting. So this, as you can imagine, unleashed huge amounts of greenhouse gases and caused Earth's atmosphere to the temperature of Earth's atmosphere to increase by 12 degrees Celsius. And remember, the goal to avoiding the worst part of climate change for us now is about 3 degrees Celsius. So this increase in temperature was huge. Plate tectonics helped keep this from destroying 100% of life on this planet. Carbon dioxide is absorbed into the ocean, filters down into the tectonic plates, which sequesters CO2 for a time, like a pretty substantial amount of time. So Earth got really lucky. If there had been two of these types of eruptions that happened at almost the same time, it would have caused a period of really intense global warming, and caused the oceans to boil off. When the water is gone, plate tectonics get dehydrated and brittle, and that system shuts down too. So, which one of these is right? Is it the sun that played a more important role, or was it a really unlucky turn of events involving volcanoes on Venus that is right? Like, which one of these, if any of them are correct, is really an open question, something that planetary geologists are really looking at. So this is where I will end with Venus. As always, there's so much more to say, but in an effort to not speak for hours on each of these planets, I will leave it here. The next lecture will be on Mars.